A Washington state telecommunications contractor can install battery systems for microwave radios, even if the microwave radios are all Ethernet 5.8 MHz. This is because the scope of work for a telecommunications contractor includes the installation, maintenance, and repair of telecommunications equipment, which includes microwave radios and their associated battery systems. The installation process typically involves several key steps. Firstly, a thorough site assessment is conducted to determine the optimal location for the battery system, considering factors such as ventilation, accessibility, and proximity to the microwave radio equipment. Secondly, the appropriate type and size of battery system are selected based on the power requirements of the microwave radio and the desired backup time. Battery types commonly used include lead-acid, nickel-cadmium, and lithium-ion, each with its own advantages and disadvantages in terms of cost, performance, and lifespan. Thirdly, the battery system is installed according to manufacturer specifications and industry best practices, ensuring proper wiring, grounding, and overcurrent protection. This may involve mounting the batteries in a rack or cabinet, connecting them to a battery charger or power supply, and integrating them with the microwave radio equipment. Fourthly, the installed battery system is tested and commissioned to verify its functionality and performance. This includes measuring the battery voltage, current, and capacity, as well as simulating a power outage to ensure that the battery system can seamlessly switch over and provide backup power to the microwave radio. Finally, regular maintenance is performed on the battery system to ensure its continued reliability and performance. This may include visual inspections, battery testing, and replacement of worn or defective components. Safety is paramount when working with battery systems, as they can pose electrical and chemical hazards. Firstly, appropriate personal protective equipment such as gloves, safety glasses, and insulated tools should be worn at all times. Secondly, the battery system should be disconnected from the power source before performing any maintenance or repair work. Thirdly, the battery system should be properly ventilated to prevent the buildup of explosive gases. Fourthly, spent batteries should be disposed of in accordance with local regulations and environmental guidelines. The maintenance aspect involves several crucial procedures to ensure the long-term reliability of the battery system. Firstly, regular visual inspections should be conducted to check for any signs of corrosion, damage, or leakage. Secondly, battery terminal connections should be tightened periodically to prevent voltage drops and overheating. Thirdly, battery voltage and specific gravity should be measured regularly to assess the state of charge and overall health of the battery. Fourthly, equalization charging should be performed periodically to balance the charge among individual battery cells and prevent sulfation. Fifthly, the battery system should be kept clean and free from dust and debris. Repairing a battery system typically involves diagnosing and resolving any faults or malfunctions that may arise. Firstly, a thorough inspection of the battery system should be conducted to identify any visible signs of damage or failure. Secondly, battery voltage, current, and resistance should be measured to pinpoint the source of the problem. Thirdly, faulty batteries or components should be replaced with new ones of the same type and specification. Fourthly, wiring and connections should be checked for continuity and proper insulation. Fifthly, the repaired battery system should be tested and commissioned to verify its functionality and performance. Regulations and codes play a significant role in the installation and maintenance of battery systems. Firstly, the National Electrical Code, also known as NEC, provides guidelines for the safe installation of electrical equipment, including battery systems. Secondly, local building codes may specify requirements for ventilation, fire protection, and seismic bracing of battery systems. Thirdly, environmental regulations may govern the disposal of spent batteries and the handling of hazardous materials. Fourthly, industry standards, such as those published by the Institute of Electrical and Electronics Engineers, also known as IEE, provide best practices for battery system design, installation, and maintenance. Firstly, NEC Section 480.2 covers battery locations, which must be readily accessible for maintenance and inspection. Secondly, NEC Section 480.3 covers battery terminal connections, which must be properly tightened to prevent overheating and voltage drops. Thirdly, NEC Section 480.4 covers battery overcurrent protection, which must be provided to protect against short circuits and overloads. Fourthly, NEC Section 480.9 covers battery ventilation, which must be adequate to prevent the buildup of explosive gases. Battery capacity is a crucial parameter that determines the runtime of the microwave radio during a power outage. Firstly, battery capacity is typically measured in amp-hours, also known as AH, which represents the amount of current that a battery can deliver for a specified period of time. Secondly, the required battery capacity depends on the power consumption of the microwave radio and the desired backup time. Thirdly, battery capacity decreases over time due to aging and degradation, so it is important to periodically test the battery capacity and replace the battery when it falls below a certain threshold. Fourthly, battery capacity is affected by temperature, with lower temperatures reducing battery capacity and higher temperatures accelerating battery degradation. Battery charging is another important aspect of battery system operation. Firstly, batteries must be properly charged to maintain their capacity and prolong their lifespan. Secondly, different battery types require different charging methods and voltage levels. Thirdly, battery chargers typically use a multi-stage charging process that includes bulk charging, absorption charging, and float charging. Fourthly, overcharging can damage batteries and reduce their lifespan, so it is important to use a battery charger that is specifically designed for the battery type being used. Battery monitoring systems are used to track the performance and health of battery systems. Firstly, battery monitoring systems can measure battery voltage, current, temperature, and capacity. Secondly, battery monitoring systems can provide alerts when battery parameters fall outside of acceptable ranges. Thirdly, battery monitoring systems can be used to optimize battery charging and maintenance schedules. Fourthly, battery monitoring systems can help to prevent battery failures and extend battery lifespan. The selection of a suitable battery technology is critical for optimal system performance and longevity. Firstly, lead-acid batteries are a common choice due to their relatively low cost and wide availability. Secondly, nickel-cadmium batteries offer good performance at high temperatures but are more expensive than lead-acid batteries. Thirdly, lithium-ion batteries provide high energy density and long lifespan but are the most expensive option. Fourthly, the choice of battery technology depends on the specific application requirements, budget constraints, and environmental considerations. Proper grounding is essential for the safe and reliable operation of battery systems. Firstly, the battery system should be grounded in accordance with the National Electrical Code. Secondly, the grounding conductor should be sized appropriately to handle fault currents. Thirdly, all metal enclosures and components of the battery system should be bonded together to create a low impedance ground path. Fourthly, proper grounding helps to prevent electrical shock hazards and minimize the risk of equipment damage. Protection against overcurrents is a critical safety measure for battery systems. Firstly, overcurrent protection devices, such as fuses and circuit breakers, should be installed in the battery circuit to protect against short circuits and overloads. Secondly, the overcurrent protection devices should be sized appropriately to handle the maximum current that the battery system can deliver. Thirdly, overcurrent protection devices should be located as close as possible to the battery terminals to minimize the risk of fire. Fourthly, regular inspection and testing of overcurrent protection devices is essential to ensure their proper functioning. Environmental considerations play an increasingly important role in battery system design and operation. Firstly, spent batteries should be recycled or disposed of in accordance with local regulations. Secondly, battery systems should be located in environmentally controlled enclosures to protect them from extreme temperatures and humidity. Thirdly, energy-efficient battery chargers and monitoring systems can help to reduce energy consumption and minimize environmental impact. Fourthly, the use of renewable energy sources, such as solar power, can help to reduce the reliance on fossil fuels for battery charging. Integration with renewable energy sources offers significant benefits in terms of sustainability and cost savings. Firstly, solar panels can be used to charge batteries during the day, reducing the reliance on grid power. Secondly, battery systems can store excess energy generated by renewable sources for use during periods of low generation. Thirdly, integrating battery systems with renewable energy sources can improve the reliability and resilience of the power grid. Fourthly, government incentives and tax credits are often available to encourage the use of renewable energy and battery storage technologies. Remote monitoring and control capabilities enhance the operational efficiency and reliability of battery systems. Firstly, remote monitoring systems can provide real-time visibility into battery performance and health. Secondly, remote control systems can be used to adjust battery charging parameters and perform remote diagnostics. Thirdly, remote monitoring and control capabilities can reduce the need for on-site visits and improve response times to battery system problems. Fourthly, remote monitoring and control systems can be integrated with other network management systems to provide a comprehensive view of the entire telecommunications infrastructure. The lifespan of a battery system is influenced by several factors. Firstly, battery type, with lithium-ion generally outperforming lead-acid in longevity. Secondly, operating temperature, as extreme temperatures accelerate degradation. Thirdly, charging and discharging patterns, with deep discharges shortening lifespan. Fourthly, maintenance practices, as regular checks and proper charging extend lifespan. To extend battery lifespan, firstly, maintain optimal temperature, typically between 20 and 25 degrees Celsius. Secondly, avoid deep discharges, aiming for shallow cycles whenever possible. Thirdly, use a smart charger that adapts to the battery type and condition. Fourthly, perform regular maintenance, including cleaning terminals and checking electrolyte levels if applicable. Troubleshooting common battery system issues is a critical skill. Firstly, identify the symptom, such as low voltage or failure to charge. Secondly, isolate the problem, checking connections, fuses, and individual battery cells. Thirdly, use a multimeter to measure voltage, current, and resistance to pinpoint faulty components. Fourthly, consult the manufacturer's documentation for specific troubleshooting steps and safety precautions. The cost of a battery system includes several components. Firstly, the initial purchase price of the batteries, which varies significantly based on type and capacity. Secondly, the cost of the battery charger or inverter, which must be compatible with the battery type and voltage. Thirdly, the installation cost, which includes labor and materials for wiring and mounting. Fourthly, the ongoing maintenance cost, which includes periodic testing, cleaning, and eventual battery replacement. Future trends in battery technology are focused on improving performance, reducing cost, and enhancing sustainability. Firstly, advancements in lithium-ion technology are leading to higher energy densities and longer lifespans. Secondly, new battery chemistries, such as solid-state batteries, are being developed to improve safety and performance. Thirdly, battery recycling technologies are becoming more efficient and widespread, reducing the environmental impact of battery disposal. Fourthly, the integration of artificial intelligence and machine learning is enabling smarter battery management systems that can optimize performance and extend lifespan. In summary, a Washington State telecommunications contractor is indeed authorized to install the battery systems associated with microwave radios based on the inclusive scope of their license. This encompasses the full spectrum of services, from initial installation to ongoing maintenance and eventual repairs, ensuring the seamless and reliable operation of telecommunications equipment. Proper adherence to safety protocols, regulatory requirements, and industry best practices is paramount throughout the entire process. This ensures both the longevity and dependability of the battery systems, safeguarding the critical communication infrastructure they support.